So this question here asks to estimate the temperature when a reaction becomes spontaneous. And spontaneity, when we're talking about chemical reactions, we must be talking about the free energy, the Gibbs free energy of a reaction. Because the Gibbs free energy of a reaction takes into account the enthalpy of the reaction as well as the entropy of the reaction. So remember that a reaction is only spontaneous if the entropy of the universe is increased. So that means either the reaction has to give off heat, which is going to heat up the universe and therefore increase the entropy of the universe, or the reaction itself has got to have a positive entropy associated with it. We have two numbers. Because we have two numbers, and they can be either positive or negative, that means we have four scenarios that are possible. So let's draw a graph here of free energy on the y-axis here and temperature on the x-axis. Let's think about a situation where the delta H is a positive number and the delta S here is a negative. So what that means is this will be positive, and then minus a negative number will mean that it'll be another positive number. Okay, so what that means is it'll be non-spontaneous, and then as we increase this temperature, this last part will become a larger and larger and larger positive number. This case here is where we have delta H is a positive number minus T minus a negative delta S. So the other possibility is that we have delta H still being positive and then our S here being positive. So then we've got a situation where we have a delta H positive minus a positive number, so we're getting more and more negative as we're increasing the temperature. So that means the situation will be like this. So this is delta H minus T delta S, and the S there is positive. So in that kind of a scenario, there will be this certain temperature where the negative nature of this T delta S will overwhelm the positive nature of the delta H being positive. So the other case here is where we have a negative delta H and we might have a positive delta S. So that's going to be spontaneous initially, and then as we increase the temperature, this delta S, because it's positive, will become a more negative number. So this case here would be where we have the negative delta H, and then we're minusing the T delta S away from it. So it's going to be spontaneous at all temperatures. The other scenario is where we have a negative delta H initially and a negative delta S, so that these multiplied together, negative minus times a minus delta S will be a positive. So there may be a temperature where this final bit gets overwhelmed. So this is negative delta H minus T minus delta S. So that's the scenario there, because these two things will overwhelm it. So that means that this one will be spontaneous and become non-spontaneous. This other situation here will be non-spontaneous, and then there will be a temperature where it becomes spontaneous. So we can see there that the point where they switch between spontaneous and not is where it crosses the delta G equals 0 axis. So that means this is a good marker. So delta G equals 0 means that we are switching between this spontaneous and non-spontaneous state. So we can use that in our equation up here, and all we need to do is work out delta H and delta S for the reaction. So we know that the heat of formation of pure elements in their most thermodynamically stable state, such as graphite and chlorine gas, are going to be 0. So therefore, we just need to use the chemical formula up here to work out our delta H. So delta H is equal to the sum of each individual product times the delta H of formation of our product minus the sum of the number of each ones of our reactants times the delta H of formation of our reactants. What do we got? We got 1 times the silicon tetrachloride, and we've got how many? 2 times carbon monoxide, and we need to minus that away from the sum of how many do we have? Silicon dioxide 910.9, and we need to add that on to 2 times carbon, which is 0, and 2 times chlorine, which is 0 as well, which works out to be 474.9 kilojoules for that reaction. So now let's work out the entropy of the reaction. The delta S is equal to the sum of the number of each one of our products times the S0 of our products minus the sum of the number of each one of our reactants times the S0 of our reactants. So again, we will see that the entropy of these things is non-zero because only a solid at 0 Kelvin will have an entropy of 0. So again, we need to do our sum there. So there is 1 silicon tetrachloride. The entropy of that is 300.6. We have 2 carbon monoxides, and the entropy of those carbon dioxides is 197.6. You take that away from the sum of 1 of our silicon dioxide for 1.84, and we have 2 of our graphites, and we also have 2 of our chlorines. And that works out to be 226.48 joules per mole per Kelvin. So now it's time to put all of this together. So our equation was delta G equals delta H minus T delta S. So we want to figure out when it becomes spontaneous, so we need to have the delta G as 0. Our delta H in this case is 474.9, and we're minusing away what temperature we need times 226.48. So we've got a positive delta S and a positive delta H. So if we look at our graph here, we have this scenario here where we have a positive delta H and a positive delta S. So it's non-spontaneous at low temperatures, and then it becomes spontaneous at a certain temperature. So we've got to be careful here, because this value here was in kilojoules and this value here was in joules. So we need this to be by 10 to the 3 to make up for that. So now we can work out our temperature where it becomes spontaneous is going to be 474.9 by 10 to the 3 divided by 226.48. So our temperature where it becomes spontaneous is 2097 Kelvin.